Electricity with zero resistance sounds like science fiction, but it's real. It's called superconductivity, and it's already at the heart of some of the most powerful technology we're building right now. Quantum computers, next-generation power grids, ultra-precise medical scanners, all of them lean on this phenomenon in some way. Here's the basic idea. In a normal wire, electrons bump into atoms as they travel. That creates resistance. That resistance turns into heat. That heat is wasted energy. It happens every time you charge your phone or run your fridge. It's unavoidable, at least normally. But when certain materials are cooled down to extreme temperatures, something strange happens. Resistance disappears completely. Electrons flow through with nothing slowing them down. No heat, no loss, just pure unimpeded current. That's superconductivity. We've known this effect exists for over 100 years. The first observation was in 1911. And for decades, scientists assumed it was a kind of all-or-nothing event. Either the material is superconducting or it isn't. Cold enough and it flips, not cold enough and it doesn't. But that picture turns out to be too simple. The real story is more interesting. What researchers are now uncovering is that there's a hidden phase happening before full superconductivity kicks in, a kind of pre-superconducting state. Electrons are already starting to organize themselves, already beginning to behave differently, before the material actually loses its resistance. And understanding that middle stage is turning out to be one of the most important puzzles in modern physics. To get why this matters, you need to know a bit about how superconductivity actually works at the quantum level. In normal conditions, electrons are loners. They carry a negative charge, so they repel each other. Makes sense. But in a superconductor, something counterintuitive happens. Electrons start pairing up. These are called Cooper pairs, named after the physicist Leon Cooper who helped explain them back in the 1950s. Two electrons somehow form a loose bond, mediated by the vibrations in the material's atomic structure. When that happens, the pair behaves according to different quantum rules. They stop acting like individual particles and start acting more like a collective wave. And that collective wave can flow through the material without scattering off atoms. No resistance. The classic explanation says this pairing happens all at once when you hit a critical temperature. But experiments keep showing hints that the electrons are doing something more gradual. There's a region as you cool down toward that critical point where the electrons seem to be flirting with pairing, forming short-lived, fluctuating correlations. Not fully committed yet, but not independent either. This murky zone is what physicists call the pseudogap phase, and it's been debated and studied for decades. What's happening inside it? Are electrons forming ghost pairs that almost work but don't quite? Is there some competing order that fights against superconductivity? Or is it an early stage of the same process, just not yet strong enough to take over the whole material? Recent work is starting to pull back the curtain on this. Using extremely sensitive measurement techniques, researchers can now track how electrons behave at a much finer level than before. They're watching how electron correlations build up, how the pairs start to form and fluctuate, and how that process eventually crosses the threshold into true superconductivity. One key finding is that the transition isn't as sharp as it looks from the outside. Resistance might drop to zero at a precise temperature, but the underlying quantum state has been quietly shifting for a while before that. It's a bit like water freezing. The surface goes solid at 0 degrees Celsius, but the molecules have been slowing down and organizing for some time before that. The observable change looks sudden. The underlying physics is more of a gradual story. So why does this matter beyond pure curiosity? A few reasons. First, if we understand how superconductivity begins, we have a much better shot at engineering materials that superconduct at higher temperatures. Right now, most superconductors only work when cooled to incredibly cold conditions, often using liquid helium, which is expensive and hard to work with. A material that superconducts at room temperature would be transformative. It would change how we transmit power, how we build computers, how we design medical equipment. Scientists have been chasing that goal for decades. Knowing what actually triggers the transition could point the way there. Second, this has direct relevance for quantum computers. Quantum computers rely on quantum bits, called qubits, that can exist in multiple states at once. Many of the most promising qubit designs use superconducting circuits. The coherence of those circuits, how long the quantum state survives without being disturbed, depends heavily on the behavior of electrons in the superconducting material. If you understand the electron dynamics more precisely, you can design better qubits. Less noise, longer coherence, more reliable computation. Third, this kind of research pushes our understanding of quantum matter in general. Superconductivity is one piece of a much larger puzzle about how electrons in materials collectively organize into exotic states. Magnetism, charge density waves, topological phases, these all connect. Understanding one helps illuminate the others. What makes the current moment exciting is the tools available now. Angle-resolved photoemission spectroscopy, scanning tunneling microscopes, ultra-fast laser probes. These let physicists see electron behavior in ways that simply weren't possible 20 or 30 years ago. The hidden flow of electrons before superconductivity kicks in is no longer completely hidden. We're starting to see it directly. The picture that's emerging is one of electrons gradually falling into quantum coherence, like musicians in an orchestra tuning up, finding the same rhythm, until suddenly the whole ensemble is playing in sync. That moment of synchrony is superconductivity, but the tuning up process matters just as much. We're still building that full picture, but each experiment gets us closer, and the payoff, in terms of technology and fundamental understanding, is enormous.